Hello, good morning. Today we will begin our discussion on the second chapter, that is electrostatics. So from the name, we know that statics meaning something that is not changing with respect to time. So we're dealing with a time independent situation here. So we're dealing with static E field for now. Today's topics will be Coulomb's law. We'll discuss Coulomb's law, and this is something we are already familiar with from 1520 or 133 that when you take it. Before we start, I want to remind ourselves the definition of the script R, and we will use script R in our notation. This kind of notation might be a little bit different than how we approach things in the introductory physics. You probably do not do your calculation of Coulomb's law, or you probably did not really do your integration using the script R. The reason that we use script R here is, as I will show later today with our calculation example, that we are able to treat the calculation of vector field. With the script R, we can treat it basically like a scalar calculation. We can break it down into different components. And then script R will make that a little bit more easier, and hopefully I will be able to show you later today. So first of all, let's just do a really quick clicker question. Is just a review and make sure that we are aware and we understand how to represent the script R. In this case, I'm asking about the R hat. It's pointing from 1, which is here. This is 1, and to another point R in space right here. Okay, so how do we represent it? I will give you guys the pool about a minute or two. You can put in your vote. Getting majority of the vote already, so another 10 seconds. Okay, any last minute vote? Okay, I'm going to close it and then let's take a look. Okay, it seems like majority of us voted for C, and there are some votes for A as well. So let's take a look. To get the R hat, right, we first need to write this vector and then divide it by its magnitude. So if we were to write out this vector, which is R minus R1, and what is R? R is X1, Y1. I'm sorry, the first one is R. So R is simply just X and Y, and R1 is X1, Y1. And you get X minus X1 and Y minus Y1. So for those of you who chose A, I think you're given the correct expression for R vector, but it's asking for R hat. You just need to remember to do the hat, we need to divide it by the magnitude, right? And you simply just need to divide that by the magnitude of R. and that gives you the choice C, which is correct. Very good. Okay, so using the script R notation, we will write our Coulomb's law in this format. So I define my origin in space to be here. And let's say I have Coulomb's law is describing the electrostatic force between 2 point charges. And let's say I have one right here, and I have another charge right here. And each of them have a position in space. This one is located at R1, and this one is located at R2. Now, of course, the separation vector between these two charges is described by script R vector. So if I want to write out Coulomb's law, I would say the force acting on the charge Q2 by charge Q1 can be written in terms of now the Coulomb's constant Q1 Q2 divided by the distance squared, right? It's an inverse square law, script R squared. And we know that the direction combined with the sign of the charges and the direction of the R hat gives you the direction of the force. So that is something we discussed previously. So here R is R2 minus R1, according to my drawings right here. It follows the head to tail method. Or you can always think of this as R is pointing from the source to the point of interest. Now, in this case, I'm interested in the force by Q1. So in this case, Q1 is my source. We can also view this as if Q1 has generated an electric field around it, and Q2 inside this field feel the Coulomb's force. So Q1 is your source. That's why R is pointing from Q1 to Q2. So that's the way, another way we can memorize where R is pointing at. So R hat is R vector over R magnitude. Just really follows how we did before. It's going to be x2 minus x1 here, y2 minus y1, z2 minus z1, and divided by the magnitude.
Dr. Ryan, may I ask how you're defining a source?
Defining a source is, in this case, I'm looking at the force by Q1. It's the agent of the force is Q1. So in this case, I want Q1 to be my source. However, if I want to say what is the force on Q1 by Q2, then I will say Q2 is my source.
Got it. Okay, thank you.
And if you have multiple of those charges, now we are looking at the one source. If I have multiple charges, Q1, Q2, and Qn. So let's say you have Q1 here, Q2 here, Q3 here, and a lot of these point charges, and they all give exert a force on this little q, for example. Then you have multiple sources. So by superposition principle, we can add up all the forces together. So if you have multiple sources, it follows superposition, where the force acting on the little q by all the sources, QIs. So to separate these sources and the point of interest, I use capital Q for my source, but it's, they're just all point charges. So how do I add them together? I add up all of them one by one, because each of them will be acting on the little q. So I simply just sum them all together. So to write it out, and here my little q, I'm just going to say my little q is at a point in space that's at vector r. let's say this is my origin. And this is at R. And each of these is at a different location, right? R1, R3, or R2, and so on and so on. So each of them have a different separation vector. And continue to write this up. Sum I from 1 to n, if you have n total charges, and 1 over 4 pi epsilon naught q times qi, divided by, now each of them have a separation vector, and this curly r is going to be r minus r little I. I'm here looking at the magnitude of that. And also you need to have the hat. Now to do the hat, I'm just not gonna write this. I'm just gonna do the hat overall. Now, sometimes we realize the hat, to calculate the hat, we need to know this vector anyway. So this is really the vector divided by the magnitude. That is the hat. So sometimes we just absorb this into the entire equation and just don't even write the hat, because that's not, you need the vector to calculate the hat anyway. So we end up with just writing r minus r I, and the denominator becomes cubed. So if you see something like this, it is equivalent to the previous expression. It's just that, you know, the hat can be expressed using the vector itself divided by the magnitude. And you can see that this is still in the, in terms of the dimension, is still, units or dimension is still 1 over meter squared. It's a 1 over r squared dependence, right? I haven't really changed the unit or the expression. So each of the script r, so each of them will have a different script r, which is r minus ri, okay? Which is always the field minus the source. Now the field, in this case, there is a point charge in the field, or you can think of this as just a point in space I'm interested in. For example, I put a little test charge Q here because I'm interested in what's going on in this point. Without the test charge Q, we can simply define what's going on in the field by saying what is the electric field at that point. Because if you know the electric field, you can simply multiply the charge by the field, you can still get the force. So a lot of times we simply are calculating the electric field. So the electric field at the point of interest, we define it to be the force on the charge, on the test charge, divided by the total amount of this charge. So this is something we have learned in our intro physics. Now you can see that everything else except the little q, if we get rid of this little q, everything else simply is going to be the expression for your electric field. So here, electric field at point, the point you're interested in, let's call it point P. So the field at that point is going to be sum of 1 I from 1 to n. You have multiple sources, you add them up, divided by 4 pi epsilon naught. You can do r hat over r squared, or you can do r vector over r cubed. It's the same thing, and the rest of it follows. E field, they are also like the forces. E fields are vectors, and it's present in the space, in empty, can be present in empty space. If you know where all the sources is located, you can always find the total E field by using superposition. And if once you know what the field is, you multiply that by the test charge Q, you can get the force that is acting on the charge. In our calculation, most of the time, we're just caring about the electric field, because once we know that, we know the feature in space. We know how, if you were to introduce a charge in space, how it's going to behave, because we already know the field. Okay, so here there are some more questions that can help us looking at the E field. It may be a little bit different from our intro physics questions, but we should be able to answer them with just our intro knowledge. So for example, I give you 5 charges. They are arranged in such a pentagon shape, one of charge at each corner. And I'm asking what is the E field at the center. I'll give you guys a couple minutes to discuss this in your small groups.
And then one question before we go into those groups. Just by convention, we use a test charge to be positive, correct?
Not necessarily, because we always, when we get the E field, we always divide that force by the test charge. So the Q, whether your test charge is positive or negative, does not affect our field, right? And our field is decided once your source are a given.
Got it. Okay, thanks, Dr. Ryan.
Sure. Okay, so take a screenshot if you need it later on to talk in your group before you join the breakout rooms. Okay, let's go for 10 more seconds. If you have last minute vote, please put it in. Yeah, so I get a message asking about whether we could use superposition, and also if we have some kind of symmetry here, can we tell that the overall field will be non-zero? You're right. One way to look at this is by superposition of looking at each field generated by each of the charges, and also argues whether some of these are stronger than the other and how do they add up. Yeah, let's take a look at our results. We'll get back to your question later. Here's is our results. So we are pretty much even between the choice A and B. Okay. So anybody would like to share with us that what they have discussed, or some strategy we can use to begin the process of answering this question? Anybody?
Well, they're all equidistant from the origin. If the origin you make to be point P.
Okay.
Then again, does that work? Could you make the point of interest your origin?
That is my point of interest because I want to know the E field at the center. Yes. So this is my
If that's
point.
the case, then they're all equidistant away from the center. You can see the right side of the cues and the left side of the cues of that pentagon. They look like they're going to cancel just looking at their distance away from the origin. But the one on the top doesn't cancel with anything. And so you're left with a non-zero answer. Is that right?
Okay. So, okay, let's try to draw one of the vectors. You're right. They all have same distance from the center, though, so they are the same strength. The E field would be the same strength. In terms of how they will add up, I see someone raise their hands. I'll get back to you real quick, but let's draw one of the vectors. So Q, let's just begin with one of them. This one, the vectors from a positive, let's assume they're positive. No, the negative should follow a similar way. If they're positive, it's generating an E field away from this charge. So it's going to be following the line between this point and this point. It's going to be in this direction. Do you agree? That is E field generated by this little q alone, right?
Agreed.
So if this one is going to be another q pointing away, the same strength, this one the same, and this one is the same. Okay. They don't really cancel. You can see that they're all pointing, the component that's pointing to the left cancels to the right. But the components pointing up is stronger than the components pointing down. So you are still left with component pointing up if you add them up. This one is the last one, gives me one going down. One might argue maybe that cancels everything, but maybe you're not convinced. Maybe you feel like, well, without calculation, I'm not so sure. Okay, so Carly, I see that you raised your hand earlier, so would you please say something or raise your question?
I was just going to mention with the top and bottom canceling, your X components would cancel with the left and the right sides, the four that are symmetrical of the left and right sides, but they have different Y components. So the four that would be at the bottom of the pentagon wouldn't exactly cancel completely.
Yes, very good. Yes. So now if we have 5 of them, do you think the E field at the center would be 0 or non-zero? Luis said 0. So Luis, would you mind say a little bit more why you think this is 0? Or are you having trouble typing, saying things? You can only type. Okay, we just added the vectors. Yes, you can do vector addition. Is there another way to make this argument? A lot of times when we do it one way, we always want to confirm it another way.
If you like overlay a circle on that pentagon, the dots are, it's not just that they're equidistant from their origin, it's that they're equidistant from each other.
Okay, so who is talking? Nathan?
Oh, Brendan?
Okay. Brendan, okay, thank you. So say it one more time. I don't quite, your audio wasn't so clear before.
Sorry, it's the points are both equidistant from each other along like a circle if you were to overlay it on the pentagon,
Okay.
and from the origin, so they should cancel out due to the sines and cosines.
In terms of the sines and cosines, so you're still looking at the symmetry and the vector addition to make the argument that they should cancel out, right?
Yes. Oh, never mind. Sorry.
Yes, indeed. They do cancel out. You can think about, okay, so this one is pointing directly down, but this one is pointing halfway, is pointing diagonally. So the component of this is going to be a little bit smaller, but you have multiple of these. You have two of these, and they cancel part of these components. So when they all add up, the component pointing up, qualitatively, they should cancel out the component pointing down. But I will provide another argument just to make it more convincing that let's pretend it is not zero. Let's pretend it's some non-zero number. Now, if it's non-zero, it has to point in some direction because this is a vector. If you're saying it's not zero, it got to have a direction. You can even assume a direction by just saying it's just some random direction here at the center. Now, which means if you tilt your head, or if you can rearrange its Q, let's rotate it 1/5 out of the way, right? You put this Q, here, you make them all rotate. Or if you are just looking at the center and you tilt your head to be 1/5 out of the way, then you must notice a change in direction of the E field, right? However, there really shouldn't be a change because if you rotate your charge, if you rotate them, you are still dealing with the exact same physical configuration. You have one charge at each corner. You haven't changed the physical setup. That should not change your answer. But we assume the direction and the rotation should change the direction. So for the only way for this conflict to go away is for the E field to be zero at the center, so that no matter how you rotate, you're dealing with the same physical setup and you deal with the same physical result in the center, which is zero. So that's another way to argue that E field should cancel at the center, which is zero. Okay, now let's say if I take one of the charge away, so you see the top one is gone, we're left with the 4. And we are asking you to calculate the E field at the center. You might wonder, okay, I'm adding up the 4 of the charges using superposition. It's getting a little bit harder to calculate. Is there another way to do this, which will give us some quick answers? So I will let you put in your votes right here. You're free to type in some chats in the chat box, or if you wanted to ask questions or talk, you can always talk out here. Okay, we have 80% of the vote coming in. Let's go for another 15 seconds. Okay, let's take a look at this together. So here are our results. It seems we all agree there's something we can calculate. The difference, we only just really differed in terms of our direction, right? Whether it's plus or minus is j hat. Very good. So anybody would like to tell us the strategy they used to calculate E at the center with the fifth charge taken away? Now to what we had earlier is when you have 4 of them, oh, sorry, when you have all 5 of them, they add up to be 0. This is what we have previously. And the follow-up question, what is the 4 of them? So anybody would like to share? Yes, I got a message. For the last one, is it because we have a perfect fine point symmetry about this point and rotating the charges around the point wouldn't change the symmetry so it has to be 0 at the center. Yes, so that is another method we talked about to answer the previous question. You have the symmetry, you're rotating the charges, you haven't changed physical setup, which means you shouldn't change the E field at the center. So only way for the E field to be not changed at the center is it for it to be 0. So how do we answer this question? What is the E right here?
I was thinking they'll have to add up to that last E5. So that should be pointing to the opposite direction of where E5 was.
Yes, very good. So E5, all 4 of them is simply just the opposite direction of the E5. Excellent. So if the E5 were here, it's generating an E field downward in the negative J hat direction. So, and the magnitude is KQ over R squared, R is A. So if it's opposite of that, which is positive J hat direction, pointing upward, very good. And also from a vector addition earlier, you have already seen that these vectors pointing in the Y hat direction because they're pointing up. Okay, very good. So for now, we have been looking at discrete charge distributions, and we know that a lot of times we are really dealing with the continuous charge distribution, and we have to use integrals. So before we further solving an integral problem, I want to be able to give you the 3 equations that we use to do a volume charge situation, a volume density, a surface density, and a line density. So so what do we do when we have a volume, when these charges, let's say they're all smeared, they become a continuous charge distribution. The summation becomes, so this was before. Hat. Okay, so this becomes the integral little dq. I'm sorry, go ahead.
Dr. Ryan, are you still, because I hear you writing stuff down, but I don't see you writing stuff down.
Yes,
Yeah, same. I don't see anything.
my share did not follow. Let me do it again.
There we go.
Okay, thank you for reminding me. So here, these little r hat, they are pointing from the source. Now, I have many sources. Each of them are a little chunk of charge dq to the point that I'm interested in evaluating my E field. So that's my script R. Now, if I'm dealing with a three-dimensional charge, how do I write my dq? In 3D, dq can be written using something called the volume charge density. And as we recall, the volume charge density rho can be a function of R because you may have different density at different location, or it could be uniform, as a lot of times we are dealing with a uniform density. So this is a volume charge density. That is the total charge over volume. Okay, so my dq is going to be density times little volume dv. I'm gonna say volume because in Griffiths, I'm actually gonna use d tau to represent it. Just that we don't get confused, v as in the potential. Here we're gonna say d tau. And whenever we do a source, something that is dealing with a source, we use a prime just to separate it from the field. So d tau, let's say you have this volume, I'm gonna draw a blob of charge. And by looking at simply a little chunk of it right here, this is my dq, okay, and is located at R prime. Again, it's the location of the source is always the prime from the origin. And you are interested in evaluating what is the E field here. This one has a location of R, and they are separated by separation vector curly R. So little of d tau is simply going to be dx prime, dy prime, and dz prime, right? If you're looking at a little chunk, a little cube. So so having expressed this using volume density, our E field now becomes, what do they look like? The E at location R is going to be the integration over this volume, right? And you can see I'm integrating over dq. dq becomes rho d tau now. And okay, a lot of times, so sometimes we do dr cube to show the volume. It's the same thing as writing d tau. Just that if you see that this kind of notation, you should know what I mean by it. This is just d tau volume over r squared, and it's in the direction of r hat. Be very careful that a lot of times we cannot do E in one integral. We have to do EX separately. We have to do EY separately. And we have to do EZ if you have a Z component. Because when you're adding everything up, you're adding things like a scalar only if they're in the same direction. You cannot add things up using integrals if you have an X and Y component together, right? So a lot of times, even though our general expression is like this, in real practice, you're doing the component by component, one by one separate. So this is for a volume density. You can see the rest of those two follows very similarly. So I already guessed what the surface charge is, right? You simply replace a volume density with a surface density, and instead of integrating over volume, you're integrating over a surface. So if you have a 2D surface, then we define a surface density to be charge over area. So little dq is now sigma. Now sigma can also vary depending on where you are. So it can be a function of r prime because your charge here on the surface. So here I do a surface r prime dq. Your charge here might be different from a surface somewhere else, right? So each of the density can be a function of r prime. And here you're evaluating what is the field at point P. Okay, and again, script R. So E is very similar from previously, but it becomes sigma, and it becomes the area, and R follows. And again, the same thing for one-dimensional 1D line charge. Line density is charge over length. So again, you know how to write this is going to be, it's just integrating over a line, lambda, simply a D length, or you can still write the R over R squared. So these are our 3 different situations. So the questions that you might encounter is always going to be either a line or a surface or a volume. So let's take a look at one question just to sort of give us an idea how to set it up. The difficulty in a lot of these calculations is to find curly R. So I'm going to give you one question. And see if we know how to find this curly R vector. So here, if I give you a ring, you have a line charge density that is in a circle, that's a ring. And you want to find the E field at the center of the ring, which is at a Z distance above the center of the circle, directly above. Which one of these vectors represent your R vector? You have A, B, C, D choices.
Dr. Ryan, could you scroll back up really quickly?
Yes.
Thank you.
Okay, so let's do this poll. Okay, I have about 80% of the vote that already came in. So let's go for another 15 seconds before we close it. Okay, let's take a look at this together. I'm going to end it now. Okay, so popular votes are A and C. Okay, and let's take a look. Now for, I think I could speak for A, people who chose for A. That might look like the E field at the center would be pointing directly up, right? So if the direction of E is given by the direction of R, then my R is pointing directly up. So what do you, maybe that is the reason that some of you used to choose A, or maybe that is not. If it's not, then you're welcome to share your thoughts. But just based on what I've said, what do you think about what I just said? Because I think the E field to the center is pointing directly upward. So my curly R must be upward. What do you think?
I mean, I can tell you why it may be wrong. Before we were talking about R pointing from the source to our point of interest, and in this case, the source isn't being emitted from the origin; it's being emitted from point D on the radius of the circle.
Yeah, okay, so always go back to your definition of R, very good, source to the point of interest. So using that definition seems to be C, it has to be C. So what was wrong with my argument? You agree that my E field at the center might indeed be pointing up?
It's tempting to say because we're looking at big R being the well, I think at least most of us have ingrained in our head that R in general is the distance from the origin to the point of interest. But in this situation, big R is not representing the distance from the origin to the point of interest.
It is, like you said, C is correct. And what I said about the E pointing directly upward is also correct. What I have sort of sneaked in is I assume that this curly R is going to be in the same direction as E. Even though we have our expression this way, you can never really just do your calculation. It hasn't been broken down into a format where you can enter into your equation or your computer program to do the integral for you. You have to break it down into components. I couldn't simply say E and R are in the same direction because I have many curly R's. Each of the source is at different location. I have many sources and they all give me a different curly R. Is when I add all of them up, I get one direction, final direction. That is the direction of E. Does that make sense? So I couldn't say that the direction of E is in the same direction as R because R needs to be breaking down into R, X direction, Y, and Z, and then you have to integrate all of them.
Right. Okay. I see what you're illustrating now. Thanks.
Okay. So I will be able to show this point a little bit better by doing this the example. So today, the last task we need to do is do a line integration, a line charge. I think that's most straightforward. And we can show hopefully I can show why do we even bother introducing script R when we can do this calculation in introductory physics already. So I present you with this problem. It's a little variation from the example you have in your book. I simply shifted the charges a little bit. So you have your a line charge right here. It's in the Y direction. You can see I highlighted a little chunk of them. That is your little source, that's DL with a DL prime length. And this little chunk is at a location of R prime. And you're interested in evaluating the E field at point P, which is on the X axis. It is at location of R. Now, in this case, R is simply just X, right? So how do you represent magnitude of R in this case? That is due to little dl as shown in the picture. So that is the first question. I will open the pool, but at the same time, I also wanted to draw the example on my notes and then start setting up. So feel free to put in your poll and as I draw stuff on the board. Okay, so I have a uniformly charged rod here. And I want to find my E field at location x00. And I need to use this expression, which is the one-dimensional situation that is given. So I want to be able to simplify the R so that I can carry on with my calculation. Seems like my screen is not updated, so I need to share it with you again. First, let me share the results. I don't want to lose this. I'm going to end the poll now, and I'll show you the results, and I'm going to share my screen again. So this is the results. We have voted. We pretty much tied between C and D. Okay, and they look very similar, C and D. Okay, and now let me share my screen again. Okay, so what do you think? It looks like it's going to be in this triangle, right? And it's the hypotenuse of this triangle. So is it going to be C or D? I all agree that this line is X. This side is X. Now, what is this side? Now, difference is this one shows DL prime. So what does DL prime represent?
DL prime represents some infinitesimal amount of charge you've taken from, I don't know, like a sheet of, like a rod, a charged rod.
The DL is the length of this little red zone here. That's not what we want. We want the location of this little chunk from the origin. So that is at the location, you can see it is in the y-axis. That's why we use y prime to represent it, because it's, again, it is at the source. So it is y prime. Okay, so this is y prime. That's why it's x squared plus y prime squared. D is correct. DL prime will be useful in expressing the total charge later, right? It's going to be used here, but not into the R script dot. So D is correct. So before I do this calculation, usually it's always a good idea to analyze and think about in what direction your E has to be by looking at some symmetry. Sometimes using symmetry, you can simplify your calculation, right? Because some of the components might cancel. So before, of course, you can just go ahead and calculate it. That's totally fine. But I always encourage you to think about the symmetry before you do the math calculation. So in this case, do you think, what direction do you think the P will be pointing at location on the x-axis? Do you think it will be in the purely x direction or y direction? Or do you think it has a both x and y direction? Because if our calculation tells me one of the component is 0, I might decide not to even calculate it.
Is this a infinite line charge?
This
Or is it just a
finite charge, not infinite, finite,
oh, okay.
with
Okay.
a total length of L, capital L.
Got it. Thank you.
Let me see, some people put in the chat, both X and Y. Yes, very good. And it doesn't seem like it's going to cancel. Yes, very good. Instead of putting the P in the middle, which might cancel out. So if you had put your P here, yes, in this case, you will cancel the Y component, but your P is here. So you can see they all have, each of the little chunk will have a component in the X and Y direction, and they do not cancel. So overall, your final E field would be in both X and Y. So E will have a X and Y component. Seems like I cannot make my life easier. I will have to end up calculating both directions. Okay, that's good to know before continue. There is no symmetry that can be used to simplify the calculation, but that's good. I can always do my math calculation and then check with my symmetry argument to make sure I didn't make any mistakes. And let's use the simplification and continue to do our integration together. Your E, okay, so your lambda here is your lambda here is a constant. Okay, so that becomes constant lambda. Your DL prime is in the y prime direction. So I'm going to simplify that in using dy. Okay. And the rest of it comes down to simplify the r. Okay. So let me try to do this. R vector over r cubed. And this is my E. So as I mentioned previously, I cannot never do this integral together. I need to do EX separately. I need to do EY separately. Okay, so here is where the script R expression comes in handy. So to do the EX, all you need to do is, okay, I want the X component, my E. So I'm simply going to say, what is the X component of my R? And I can follow through with the calculation. Okay, now if I wanted the Y, I'm just going to take the Y component of my R. And the rest follows. Without the script R in introductory physics, what you would have done is you wanted to break it down into components. You want to look at, okay, one of them have a DE here. I want the DEX. So I need to find out the cosine theta and go back to find the cosine theta and put in the cosine theta. So that's what you would have done in intro physics. You can still do it this way, but with the help of script R, you can treat this entirely in more of an algebraic way instead of looking at the diagram. So we just need to know what is R is. We need to write out what is vector R. It has an X component, a Y component. Now we don't have a Z component. So we know what this is. I can just plug it in like an algebra. Okay, so R is R minus R prime. So please help me write out the R. How do I represent this?
Right off the bat, it looks like it should be x minus y hat. Or
Okay.
y prime, I apologize.
Okay, so R is x0, 0. Do you agree?
Uh-huh.
Okay, so it's an x direction only. So R vector is x0, 0. R prime vector is 0 and y direction y prime 0. Do you agree?
Mm-hmm.
Okay, so R minus R prime becomes x minus y prime and 0. So this is my script R, which makes, we already calculate the R magnitude to be x squared plus y prime squared. Now the Rx direction is going to be x, y direction going to be negative y prime. So that helps me simplify my calculation. Let me continue. My E sub x is 1 over 4 pi epsilon naught. Now lambda constant, I pull it in front of my integral. Rx is simply x. So I have x dy prime, and I have x squared plus y prime squared. The square root of that to the power of 3. So I have this. So this is my E sub x. You can see I did not go back to my diagram and didn't really bother with looking at cosine theta. If you have done that, you will end up with the same expression, cosine theta, which is x over r. You'll get the same x here. and you'll get an r on the denominator. So e sub y, if you were to calculate it, is the same thing. So it's going to be negative y prime p y prime over this. So my question for you guys is, we only have time to do one here in class. Let's just work on the e sub x. My question for you is, what is the variable we're integrating over, and what are the limits of this variable? So what are we integrating over?
dy prime.
The y prime part, yes. Why is it not the x? So when you integrate something,
Because there is no charge along the x-axis. It's all along the rod.
yes, you're integrating over your source. You're sourcing the y, very good. So you only need to care about the y prime integration. And x here, you treat it as a constant. And just let's focus on the y prime. And where are your limits?
From 0 to the length of the rod.
Okay, so we've been 0 to L, excellent. So here
0 to L.
I'm pretty much had set everything up. At this point, you can go ahead and enter this into your calculator and do your integration. You don't, the physics part here is already done. Until we get a result where you can evaluate whether it is reasonable or not by looking at the limits. So our job here is done. In physics, the rest of the is math. See if I can add a page here. I couldn't insert a page exactly in between here. Let me try some. Keep inserting page above it. No, anyway, I'm gonna go to the bottom of the notes to write this out. Okay, I end up with the expression. This is what I need to calculate. I'm not gonna do the calculation, but I'll give you a hint, and you can finish it off by yourself. Or you can look at my notes later. So the hint is, by looking at this, x and y prime, I will let y prime to be x tangent theta. So I change my dy prime to x over cosine theta squared d theta. And this thing became x to the power of 3, 1 over cosine theta to the power of 3 over 2. So you can change your variable that way, and then the results is going to be the x at this location is going to be lambda over 4 pi epsilon naught x y over y prime over x squared plus y. And these are the limits. Once I plug in the limits, I get this result. You can see the final expression has x in it as a variable, which makes sense because your E field is located on the x-axis. As you go further or closer, the E field would change as your variable x changes. So your final expression does have x as a variable, which makes sense. Now, once you get this result, you might wonder, did I do everything correctly? Did I make any mistakes? So we wanted to always reflect on results to see if it makes sense. Unit-wise, we can see that the top one has a unit of Coulomb. This one has Coulomb. And this x times square root of x squared gives us meter squared. So I do have the correct units for the E field. So unit check. And it's positive. We check the sign, it's positive. I have a positive charged rod. So that is correct. And then I want to check the limits. So what might be some limits that you wanted to look at? Limiting cases.
The limit that, oh, never mind, sorry, I'm looking for X.
Limits. You can check limits.
Is it? Oh crap! Is it It's one dimensional. Is it charge per coulomb? Or I'm sorry, charge per length?
I'm sorry.
Oh no, I thought you were asking for the units of our E.
Oh yes, unit I've already checked. It's good. I got
Oh,
yes.
oops, sorry.
I got the constant, and I got the Coulomb. I got meter squared. So that is correct unit. Yeah, someone said 0 and infinity. That is obviously units we wanted to look at for x equals 0. I would say yes, but sometimes we wanted to narrow it down a little bit more to be more accurate. So because, okay, so x equals infinity. If you put in infinity here, your result go to 0. And you say, okay, I think that is correct. But it's not, it's too like, it's not fine-grained enough. For example, if you had made a mistake of getting a result of something x, like, or instead of L squared, let's say you have put in something else, I don't know, or if you had messed up, you have a wrong dimension or something, you still get the unit go to 0, but it's not really fine-grained as you want. But there is something in terms of limiting cases that we do know that as you go further away from the source has a total length of L, and here you are at a distance x away, right? So when is at a location where x is much more than L, then your source looks to you like a point charge. So L, the spread of L doesn't seem to matter as much. So L looks like your source here should look like a point charge, which means when you do your calculation, you should get an expression that's just like a point charge. So let's try to evaluate this particular limiting cases. It's a little bit more fine-grained than just doing infinity. So x larger than L, you know, there's a common trick we always use as you will encounter a lot of this later on in your homework is you simply always do a Taylor expansion and you do limiting cases. So here, this is what we want to expand over. When x is much larger than L, then L over x is a small quantity. So I want to be able to use that. I want to have x over L showing up in my expression. So I can manipulate this to make it to show up by doing this. So you can see L over x is showing up in my expression. I'm going to treat that as epsilon. Epsilon is L squared over x squared, which is a very small quantity. So I can go ahead and do Taylor expansion around this point. So this becomes 1 over x square root of 1 plus epsilon. So you can see the thing we need to expand is this guy. 1/2, sorry, negative 1/2. To remind ourselves, this to the power of n can be expanded in terms of in this format, 2 factorial, and we have further, and so on and so on. But I usually only need the first couple of terms. I don't need to expand it I can ignore the high order terms. So in this case, 1 plus epsilon to the power of -2 is going to be 1 minus 1/2 epsilon. So let me simply use that in my expression. E, when x larger than 0 as an L, the limit becomes lambda L 4 pi epsilon naught x. And this becomes 1 over x, 1 minus 1/2 L squared over x squared. And you can see the first order term is simply lambda L over 4 pi epsilon naught x squared. Okay, so what is lambda L? Lambda L is the total density. The density times length give you what? Charge, right? The total charge Q. And x squared is the distance from your source to your point, which makes sense. If I'm going further away, this looks like a point with a total charge Q with a distance of x, right? So what is the point charge at the total distances away? Is 1 over 4 pi epsilon naught Q over r squared. So this becomes like a point charge. So my expression can reduce to that, makes me feel more confident that I have done my calculation correctly. So yes, obviously we do want to check infinity. We want to check 0 because at 0 you should blow up. You're at the location of your source, your results should blow up. And I do have those behavior, but more importantly, check something that is a little more fine-grained, that it behaves like a point charge when your x is larger than L. So that is all for this particular question. And you can do the same thing for the y component. And you can also go back to do the introductory physics way and just to see if you prefer to do it, break it down into components by looking at the geometry, or if you prefer to simply do it in the more algebraic way, like how we did it here, by writing out my r, taking out the x direction and x component and the y component. Okay, so that's all for today. I have office hour later today and tomorrow. And if you want to ask questions, feel free to come in. And I'll see you guys on Friday. Okay?
Dr. Ryan, as for your office hours today at 3, I'm curious, will this lecture be posted, or at least the notes be posted before that office hour?
I would think so. Sometimes, you know, the videos take a long time to process.
Right.
But I would hope to have at least the notes up.
Okay. All right. Brilliant. Thanks so much, Dr. Ryan.
Thank you. Thank you guys. See you on Friday if I don't see you later.
Thank you, Dr. Ryan.
Yes, thank you, Dr. Rand.
Bye. Thank you.